Okay, that was a long first half, so maybe we need to take a short breather or something. But um, are there any questions about the reduction? So that's why I said at the very beginning, I don't expect any of you to pull that out of a hat or anything, or to be super clever and think of something like that. The reduction is simple, but there's a lot of details there. And all we're really doing is we're emulating all the satisfying assignments in one graph. Oh, sorry, all the possible assignments to the variables in the graph. And then if there's a satisfying assignment, then we can resurrect what the Hamiltonian path is and the other way around. So if I give you the Hamiltonian path in the resulting graph, then I can find what the satisfying assignment actually was. And then therefore, that proves that it's the right kind of reduction. But any questions about the actual reduction itself? So the details are not really that important. It's just the overarching idea about having a variable and a clause gadget and then connecting them up in some way. Variables, we need to simulate the two possible occurrences of the variable. And then for the clause gadget, we just need to have one way representing, oh, we're seeing the positive version of this variable, and then the other one representing we see the negative version. And that's all we really need. And then to handle the details is when we introduce that buffer vertex and other things. Any other questions about it, though? Okay, so what did I ask you to think about right before the break? Undirected. So this problem is called UHAMPATH. So I guarantee you this reduction is way, way easier than the other one. So this is G, and then G is undirected and has a Hamiltonian path. So it's pretty simple to see that this is also an NP, because for almost exactly the same reason that HAMPATH was an NP, because the certificate would just be the path itself, and then we just check, because it's undirected, the certificate verification is exactly the same. But now we can just go in either direction of the edge because it's undirected. So it's definitely an NP. Do you think is NP hard? It actually seems like it is. So think about it from the perspective of the graph that we made. So we forced, in the direction of the edge, we forced to go out of one vertex and into another. Maybe what the undirected graph could do is emulate what the directed graph is actually doing. So if I take a directed edge, then we could, in the undirected graph, have a vertex representing the outward direction of this vertex, so I'm going out of a vertex, and another version of a vertex where I can go into that vertex. And then if I want to be at a vertex, I can go from the in version to the out version. So do you think is NP hard? It seems like we can reduce from the directed version of HAMPATH. So what we're going to show is NP hard, and what we're going to show, or how we're going to show that, is we're going to say that HAMPATH, the directed version, reduces to the undirected version. And then that, of course, will show that it's NP hard, because HAMPATH is NP complete. Okay, so remember, we're given a directed graph. So here, the directed graph may not look anything like the constructed one we did before. It could be any arbitrary directed graph at all. But from this directed graph, we got to produce a undirected graph that the first one has a directed Hamiltonian path if and only if the resulting undirected graph has a undirected Hamiltonian path. So we got to produce a G prime, so some other graph that is undirected, such that either they both have a Hamiltonian path, either directed or undirected, or they both don't have that type of Hamiltonian path. Okay, so how can we actually do this? Well, HAMPATH says that it starts from some vertex and it ends at another vertex. Well, let's see. What are we going to do about that? So suppose that I want to take this edge right here. So let's call this xi vertex and xj for the other vertex. Well, that just means that we're going out of one vertex into another vertex, right? So you may think, well, let's just make an out version and an in version of every vertex and then just connect them up accordingly. So let's try that. So let's say that we have an xi out right here, and then an undirected edge to xj in. And then, of course, we'll have a version of xi in for the same reason, and an xj out for the same reason. And then it makes logical sense. If I'm going into xi from somewhere else, then if I want to go out to somewhere else, I better go from the in vertex to the out vertex and then proceed elsewhere. So it makes sense to have an edge like this. Question for you. Could it be possible that since it's undirected, xi in is connected to other places? Is that possible? Yeah, certainly. So what could we do? We could do this and then go out like this. And I didn't go through xi out because it's undirected, right? So that could be an issue. And then maybe I can go through some convoluted path here, and then go this way, and then through here, and then out this way. And so I'll visit every vertex this way, exactly once with no repetition. So there's clearly something wrong here, right? We're not emulating, you must go through this way. What could we do about that? Let's do a similar idea that we did for the directed case. So let's go back. For the directed case, I could take either of these two paths down, but I can't just connect them up at the bottom. I had to have these two sets of vertices in the middle that go either way. And then once I go down here, if I went down to the bottom vertex, won't I miss all the vertices this way? Well, even if I came back there somehow, then I still got to traverse them, but then I already visited one of them. So in fact, let's do something very similar here. Between every pair of the in and the out vertices, let's add a new, let's make it blue. Let's add what is called a mid vertex. So an xi mid vertex. And I know they're close to each other. But let's connect them up this way. Then an xj mid here. Well, I still am allowed to do that red path that I have here. But instead, of course, I'm going through xj mid this time. But won't I miss a vertex? Yeah, what vertex will I miss doing this? xi mid. Because if I even tried to go that way, then I'll see xi in twice. And that's not allowed. So in some sense, this forces us to go through the in vertex first. Actually, that's not true, but we want to go through the in vertex. Then if I ever touch that in vertex, I must go through the mid vertex, which means I must go through the out vertex. So I must go the right way. But could it be possible that I entered the out vertex first, then the mid, then the end, because it's undirected. Right. So that's entirely possible. So for a directed Hamiltonian path, what are we going to do? So remember, I still can start at any vertex. So what we're going to do is we're going to look at this. We're going to say that we're going to have a vertex called start. So this is not the same thing as what Sipser has. So I'm going off of my own way here. And an end vertex. And then what we're going to do, so I'm going to do this in purple, is the start vertex is going to connect to every end vertex. Every end vertex. And then every out vertex is going to connect to the end vertex. So that must mean if I'm going out of a vertex, then the only way I can ever hit the end vertex at the very end is, this will be okay. So if I have a Hamiltonian path, then I have a sequence of in, mid, out, then I just plunk on start at the beginning and end at the end. And then therefore I have a Hamiltonian path. What about the other way? Well, I don't have to start at start here. But if you think about it, then since there's no direction on these edges, then, actually no, you can't guarantee that. I was going to say that start must appear somewhere in that list because it's a Hamiltonian path in this graph. And so what you do is you put it at the start of the resulting Hamiltonian path, which must go through the end vertex. But that means that there must be a cycle in this graph, and I can't guarantee that. So the way that Sipser does it, which I think is the right way now, is for the UHAM path, we must insist that we start at some vertex S and end at some vertex T. So a Hamiltonian path that starts at S and ends at T. Note for the directed one, we did not need that because the resulting graph that we made had nothing coming into the top vertex because of the direction on the edges. But here there's no direction. So in fact, I need to say what the start and the end vertex are. I could do the exact same thing for the directed graph, but I don't actually need to. But here I actually do. So here, what we're going to ask, the result is, so the result here is, well, I'm looking at G prime, and I need to start at the start vertex and end at the end vertex. So I'm enforcing you to start at the start vertex here and end at the end vertex. And the correctness follows because the one direction we've already showed, if there's a Hamiltonian path from start to end in this graph, then we go from start to some in vertex, which means we go to some mid and out vertex by definition, which means that we traversed one of those directed edges in the other graph. And then all the directed edges follow from there. So in fact, this is a very short but correct reduction. And does it run in polynomial time? Well, for every directed edge, I just add one more vertex. So there are only polynomially many edges, so I add only polynomially many vertices. And so, and two more, but again, that's polynomial. So in fact, what can we conclude about UHAMPATH? It's NP hard. So because of that, and because it's NP, we can say that UHAMPATH by that is NP complete. Sweet. So even the undirected version of this problem is NP complete. I know that there are some problems where the directed version is NP complete, but the undirected version is, actually no, that's not true. So for any problem where the directed version is NP complete, is the undirected version NP complete too? Pretty much. Actually, you can't guarantee that, but why does it seem intuitively true? Well, if we have an undirected edge here, can I simulate that by directed edges? Yeah, it's pretty easy. So I just have one directed edge in both directions, and that simulates an undirected edge. So, in fact, if I have a NP-complete problem for a undirected version of the problem, then the directed version of the problem is NP-complete because of that reduction right there. I just transform it. But the other direction, some problems, I believe, are NP-complete for the directed version and polynomial time for the undirected version. I'll need to look that up, but I think that's true. But any questions about this reduction?
You didn't specify a start and state.
Then I can't necessarily imply anything. Yeah, because that would imply if I could cyclically shift the order of the vertices in the HAMPATH such that I start at start and end at end, then that means that there's a cycle in the graph, but I can't guarantee that there was an undirected cycle at all. It may be a tree for all I know, but yeah, so I have to specify in the undirected case what the start and end is, but for the directed one, because of the way that the constructed graph had, I don't have to, but of course I could say you start at this vertex and end at this one, and then in the directed reduction we just specified the top one is start and the bottom one was end. And so the reduction there, if I did specify that, would be easier because it would be from the out of the original start vertex to the in of the end vertex. So if I made an out and an in of every vertex, including the start and the end one, then I just ask, is there one from the out of the first to the end of the last? And then that would be a reduction. Yeah.
So two out vertices cannot have the edge in the because
Yeah. So if I have a edge from xi to xj, then it must go from the out version of the I vertex to the in of the j vertex. And then for the in and the out versions of each vertex, I add a mid in the middle and connect the mid only to the in and the out of the corresponding vertex. And that there are no other edges. So I look at every directed edge, then it goes from the out to the in of the corresponding vertices.
And you go over why the mid was necessary?
It was necessary because if I did not have it there, then if I had something like this, then I could theoretically just go from the in vertex to some other vertex, maybe the in of another vertex, and then continue out, and I can visit the I out vertex, and then keep going. And then I would still have a Hamiltonian path in the undirected graph, but that might not correspond to a directed one in the original directed graph. So that's why if we put this, so let's go back. If I add this mid vertex there, then if I took the way to go to the in vertex, then go some other direction and not go through the mid vertex, I must see the out and mid vertex because it's a Hamiltonian path. I must see every vertex. But if I went to the out vertex, that's the only way I could ever enter these two vertices, then I must see mid, but I've already seen the in vertex.
So if you go from in and then out, like on not straight, you have to go to the mid, but you will end.
Yeah. But you may ask, well, I could theoretically go through the out vertex, then the mid, then the in, because there's no direction on the edges. So that's why we have the start vertex there, to say you must start at the start and go to an in vertex somewhere, then the mid, then the out, and then the correctness carries all the way to the end. Okay? Any other questions? Yeah.
Can you think of the mid vertices like the original ones in the HAMPATH, kind of? Like they represent the original
In some sense, yeah. Yeah, you could think of it that way. Like you're finally visiting this vertex. Yeah, you can think of it that way. Other questions? Well, all we're doing was we're just emulating the directed transition with undirected one. That's all we're doing.
So does a UHAMPATH have 3 times the number of vertices as a HAMPATH?
About 3 times, yeah. So, but just some polynomial number, yeah. Other questions? Cool. So, in fact, I think we're done with the time complexity stuff. So, we've been talking about time for 1.5 lectures, I think, a little bit more. And we've been talking about this P and NP thing, about why they're different. And of course, in this day of big data, right? So you're working with a lot of data. You're now not necessarily concerned about how much time something takes, but rather how much space something takes. So if I am looking at a Twitter stream, for example, I can't ever store all of those tweets. I can only see them as they're flying by. I can never store all of them. So you may want to know, well, if I restrict how much space you use, but I don't restrict how much time you use at all, what kinds of things can we solve in that particular model? So now we're going to talk about space. Space, but unlimited time. So there are classes that are mostly researchy based, where you limit the amount of space and the amount of time that you use. So those are more specialized. Here we're going to enforce how much space you can use, but we're not going to restrict anything about how much time you take. Okay, so you can take as much time as you want, but you have a fixed amount of space you can work with. So just like with time f of n, where we said that set of all languages that can be decided by some Turing machine that runs in f of n time, we're going to do something very similar here. So we're going to say that space of f of n is the set of all languages decided by a Turing machine or algorithm, whatever, that uses O of f of n space, and by this we mean number of tape cells, although it's not really that important, because up to a constant it doesn't really matter. Okay? Okay, hopefully we have enough time for this. And then correspondingly, we'll call n space of f of n to be the same thing, but a non-deterministic Turing machine. So just like with NP, it's the same idea here. You need to be a little bit careful and say that all computation paths cannot use more than this amount of space, but we're not going to really worry about that here. But we're just going to say space of f of n is just deterministic, how much space you use, and non-deterministic space is how much non-deterministic space you use. So what about regular languages? So how much space do they take? Well, it actually really depends on what you're thinking of as space. So what does the space actually here mean? So remember, for regular languages, for DFAs, we're never modifying the input. So should we even consider that space? I mean, you could. There's nothing wrong with that. So there are models where you can say, oh, you can read and write on the input tape, or sometimes where you say, no, you can't actually write on the input tape. You can only read. So we could comfortably say all regular languages are in space of just n. Even if we take the entire input into consideration, it's only linear space. But if you just removed the input from consideration, well, the things I only really need are, so actually this gets into technical things, but well, what do you need for the DFA? You need to remember what state you're in and what character you're reading, right? But you need to also keep a pointer to the original input to know where you are on the read-only input. So if you're not considering the input and you're not changing it, you need to remember where you are in the input. So in fact, well, if I have n things in the input, what is the size of a pointer that could address n bits of memory? It'd be log n, right? Because if I have 2 to the n memory cells, what is the size of a binary integer I need to address all 2 to the n things? Just n, right? Because if I assign all 2 to the n possibilities, then that's all 2 to the n memory locations. Same idea here. If I have n cells, then I only need a constant times log of n amount of space. But that's getting into detail that we're not going to consider. But you can think about, well, what if I didn't consider the input? But for here on out, we're just going to say f of n is always at least n to make things easier for us. So we won't worry about the input not being considered or something like that. If you look at chapter 8 in the Sipser book, there's something called L and NL, which represent log and non-deterministic log space, where you do have the function of space here not considered for the size of the input. Because the input size is n, so therefore the amount of space you use must always be at least n. But if you remove that from consideration, what could you do in, say, logarithmic space, that sort of thing. But that's getting into detail we're not going to consider. Well, what about the languages recognized by LBAs? Linear bounded automata. Well, they never use more space than what the input is provided, right? Because it'll just halt and reject if it tries to. So what space class is it in? Space of n. Cool. So in fact, this is pretty powerful, right? So even for n cells, we can actually recognize quite a lot of things. All the things recognized by LBAs, for example. So that encompasses a lot of things. So you may wonder, well, if we consider the following definition. So if we look at something called PSPACE, so this is just the polynomial time analog for space. So instead of polynomial time, we have polynomial space. So it's the same thing as before, but for space n to the k and NPSPACE for a non-deterministic version. I have no idea why they're on all caps, but that's how they were defined, and that's how people still use them. So, so PSPACE is just polynomial space, and PSPACE is the non-deterministic version. Well, we don't know whether P is equal to NP, right? No one knows that. But what about PSPACE and NPSPACE? It seems like we're going to run into some kind of issue here, right? It's where NPSPACE could have an NPSPACE complete problem, and we don't know whether that's in PSPACE or not. But let me convince you of something. Hopefully a lot of things, but especially this. If we're running a Turing machine on some input and we want to run this in polynomial time, if I run a transition, that amount of time is gone, right? Am I going to ever recover that time? Consider this. If I use some space on the tape, and let's say I delete or make blank, if you want, some cells on the tape, can I reuse that space? Yeah. So in fact, space is going to behave a lot differently than time because I can reuse space, but I can't reuse time. So that's actually one of the reasons why P is so different from NP, because you can't reuse time, but here you can reuse space. So we're going to actually prove, hopefully by the end of today, a very powerful result. So this theorem is called Savitch's theorem. So this is actually a really famous theorem that implies that P space is equal to NP space. But we're going to prove it in even more strongly than that. So what we're going to show is this. So if I have something that runs in non-deterministic space of some function, whatever that is, then that's contained in, meaning I can make an algorithm for this, in deterministic space of the square of f of n. So if I use constant times f of n space in non-deterministic space, then I can find a deterministic algorithm that only uses the square of that, which is pretty cool. Okay, anyone have any questions about what this means? So every f of n non-deterministic space machine that you could ever make, you can convert it to a deterministic one with only a slight amount of increase in the amount of space you use, a square. So this proves that NP, because of this, NP space is equal to P space, because if it runs in NP space of n to the k, for instance, then I can make a deterministic algorithm that runs in n to the 2k. But that's just another polynomial. Cool. So how are we going to ever prove this? Remember, could you reuse space? Cool. So how in the world are we going to prove this? So let's, for example, let n be any non-deterministic Turing machine running in O of f of n space. And then we'll want to convert it to a deterministic algorithm and all that stuff. So what are we going to do here? Well, let's see. If I have, let's say, c times f of n space, so c is a constant, for example. Well, how many possibilities could ever appear in the c times f of n space? Well, how many things can I put on the tape in c times f of n space? Well, if we are sloppy and say there could be 2 things I can put in every single cell, well, how many things can I put? What are the possible tape contents of c times f of n in length if I can put 2 things in every single cell? Well, it's 2 to the power c times f of n, right? Because that's just how many things I could ever put into c times f of n space. So there are, so 2 to this, although this is not completely accurate, but I'm going to be a little sloppy here. So there are 2 to the c times f of n different configs of length c times f of n. If I could put more things on the tape, then I can just increase the constant up top, or maybe increase the function by a constant or something like that to handle if I have more things on the tape. But I'm just going to be a little sloppy for this. Okay, well, let's see. Suppose we have this. So let's say we have the start config up here. And let's see, we have the end or any except config way down here. How long could this gap be? How many steps could I take? Remember, unlimited time. Well, if I have more than this number of configs that I've seen, do I run forever? Because I'll see something again, then in some sense, I'm going to run forever. So let's say that this is 2 to the power, let's see if I got this right. Yeah, c times f of n. And of course, the amount of space I use is, the horizontal part is definitely c times f of n across. So that's no issue. Well, maybe we could try remember the non-deterministic Turing machine conversion via the computation tree approach, where we tried breadth first search. We just enumerate all configs I can see after 1 step, then after 2 steps, then after 3 steps, and then after 4 steps, and then just keep going until I see an accept config or I run forever. What's the issue with that here? Well, I gotta write those configs down to remember them so that I know what to do after the next step. Well, if I have an exponential number of configuration or runtime I could ever see, won't I need an exponential number of configs to write down? So if I have 2 to the c times f of n amount of steps I could ever see, well, don't I need to write down 2 to the c times f of n at least number of configurations if we tried this breadth first approach? Please say yes. So let's just refresh ourselves. So remember the computation tree approach. So if we have a couple of configs that we can see after 1 step, and then we explore this breadth first search, maybe the first one doesn't get us anywhere, then the second one gets maybe 3, this one gets us 1, this one 2 maybe, and then this one maybe had 4 more, and then this one has 3. So of course I would need to store at each point these layers, right? I need to store the configuration along the way. There was no issue before because we didn't restrict the amount of space we can use. We just wondered whether it was decidable or recognizable or something like that. Here we're restricted on how much space we can use. So I can't use this approach. Well, that sucks. Any other ideas? Question, can we reuse space? Let's think about it for a second. So let's suppose that, so I'm just only supposing this for a second. It'll actually be true, but let's suppose it. Suppose that there's some config right here in the middle. I'm going to call it mid. And let's say that I can get from the start config to the mid config, and I can get from the mid config to the accept config. Can I get from the start to the end? Yeah, if I can go from the first to the middle, then from the middle to the end, we're all set. Can we reuse space? This is where it gets important. So once I do this computation, let's assume, do I need to remember it? No, I just need to store a 1 to represent, yeah, or a 0, depending on whether I can get from start to mid. And then delete all of the space I used and then reuse it for the mid to the accept one. Well, the same thing is true if we have some middle in between up here. So let's call it mid prime up here. Then the same logic applies. I have a start and a mid here. Then if I can go from start to the mid prime and from mid prime to the mid, then I can say I can go from start to mid. If I can go from start to mid prime, then I just delete all the space I used and put a 1 there. And then I carry on. Well, that means I'm going to have to break this in half too, and then half again, and then half again, right? how far do I have to go down? Well, let's see. If we break this in half every time, and I have 2 to the c times f of n things, how many times do I have to break it in half? Well, it's the log base 2 of the amount of things I need to look at. Remember, binary search. If I cut a list in half, then do I need to look at the other half? If I'm looking at one, do I need to look at the other? No. Then I cut the list in half. Well, if I want to find something, how long does it take for binary search? Log n. So the n here is 2 to the power c times f of n. So what is the log base 2 of the amount of steps we could ever possibly take? C times f of n. Oh, but oh no, I'm guaranteed that we run in at most c times f of n space. But here's the brilliant thing. Does the constant in the first for the NP-space machine, the n-space machine, is it the same constant for the deterministic machine I built, necessarily? No. So in fact, even though I could use c times f of n space, I just make the constant larger for the machine that I'm building for any additional computations that I actually might need. Ah, that's pretty cool. So here's what we're going to do. So we're going to make a procedure can yield. And it's going to take 2 configurations and some number t. So what this intuitively means is that C1 and C2 are configurations, and this function will return true if and only if C1 can ever get to C2 via at most t transition, the t transitions of the machine. Okay? Well, let's see. What if, so the first step is, what if t is equal to 1 step? Well, can C1 yield the same configuration in 1 step? Or at most 1 step? Certainly. So if I, at most 1 means 0 or 1. So if I have 0 applications of a rule, 0 applications of transitions, then the same configuration can yield itself. So if either C1 is the same as C2, or C1 directly yields C2 via a single transition, then accept, otherwise reject. Okay? So this is the base case of the function. So if we keep breaking this down, eventually we're going to hit 1, and then we just say, oh, can you get that in 1 step? Okay? If you get there in 1 step, or at most 1 step, you're all set. Question is, where did these configurations actually come from? Well, the start one comes directly from the machine and the input. That's no issue. What about the C2? So it's actually going to be handled by something. Well, think of it this way. Do I know what the mid configuration is? It's between. Well, suppose I know the start and the accept config, whatever they are. Do I know what the mid config is? No, like what the actual contents are. I know how long it should take to get from one to the other, but do I know what the contents are? No, because something weird could happen in the middle, and then eventually something will get us the accept config. But could I try all possibilities? Sure. So if I try all possibilities and delete the space if it doesn't work, great. If not, then if it does actually work, then we just found a mid config. And then we break it up in half again. So what we are going to do is, in this case, t must be larger than 1. Then for every config mid using c times f of n space, although the c doesn't actually matter here, then we just say, oh, can you get from C1 to mid? And can you get from mid to C2 using T over 2 transitions, right? Because I'm breaking it in half. I'm doing a binary search. So here, run, so as a recursive call, can yield of C1 to mid of, technically here I should put either floor or ceiling of t over 2 because t might be odd, but for this case we can assume that t is a power of 2 because the constant will take care of that. But the more important thing is that we're breaking this up halfway through and saying, can you get from the start to the mid, this particular mid, in t over 2 or fewer transitions? And then can you get from mid to the resulting one, C2, in at most t over 2 transitions? Great, and I haven't done the second one in yet, which is run can yield of mid to C2 of t over 2. And then, of course, we say if both tests accept, then we accept ourselves. But then if we've tried every single config for mid and none of them work at all, then could the C1 yield go to C2 eventually? No, because we've tried every possibility in the middle and it must go through there somehow. But if we've tried every possibility and none of them work, therefore, C1 cannot yield C2. Okay, so then at the end we just reject because we've tried every single possibility at this point. Question is, it's fine when I have a C1 and C2 in the T. That's fine. That's well defined. But how do I start this? Like, what's the starting call to this? Well, what should I must start with? The starting configuration. So that's easy. So the machine M, the machine that we're building is whatever input W it gets. We try to run. So this won't work, but I just want you to think about it. Run can yield of the starting configuration, which I'll call C start, which depends on the start state of M and the string W. But the details aren't important here. But what is the resulting configuration I need to worry about? Well, the accept state can be anywhere, right? It could be anywhere in the resulting final step, right? It doesn't have to be in a particular place. So do I know what the configuration is at the end? I know it contains QAccept, but do I know the contents of the tape? No. Could I try all of them? Yeah, let's try all of them. So that's actually where the issue is. So let's do this. And then we're going to, for all possible accepting configs, so that means it has the accept state in there, of length c times f of n because that's how much space the machine actually does use. And then let's call the actual config, let's call it c except. And then all I need to do is run can yield of the start configuration, which is unique, to c except. And I know the runtime because I'm guaranteed that by the machine. I'm guaranteed it runs in at most 2 to the c times f of n number of transitions. So here I put 2 times c to the f of n. And then if it accepts, then we ourselves will accept. And then if we tried every accepting configuration and none of them work, we reject at the end. So let's just recap. So the idea is let's just break up the possible computation in half. And then, well, I don't know what the middle configuration actually looks like. But the idea is correct that we delete the space once we've used it in the top half to reuse it for the second half. But ignoring the space requirement, if we have one transition, we just look up, can you actually do this in one transition? And the machine's transition function will tell us that. And then if we have more possible transitions, we break that up in half. And then we say, oh, can you get to the middle part in t over 2 steps? And then from the middle to the end in t over 2 steps. We try every possibility because we have unlimited time. And then we just accept if both of them work. And then for the actual machine, we just run this procedure for every possible accepting configuration, and then we know how long it should take. Any questions on that? Have we proven the theorem yet? You know by the tone of my voice it isn't. Why haven't we proven this? Yeah.
Sorry. You're trying to say that it runs in C definite space, right?
I'm assuming that about the machine, yeah.
Okay.
So why haven't we actually proven the theorem statement? Did we show it runs in F squared space? We haven't shown that at all. Well, let's see. How many times am I going to break this computation up into halves? How far can I go down? How many layers? Well, that's how long the entire thing is, but I'm breaking it in half every single time. But isn't that just c times f of n by definition? Oh, so that's how many layers I'm going to keep digging down into this can yield function until I hit this if t equals 1 thing. So I'm going to go down c times f of n times. Well, how much space am I going to use for each one of those? Well, for each one of them, I'm going to use c times f of n space to hold the middle configuration in memory on the tape. So I'm going to have c times f of n space to handle the recursive calls because I need to have something to help me with that. But I also need for each one of them to handle the middle configuration, right? Because I need to store that there to handle when I do the second call. I need to store the mid somewhere. But do I need much else other than that? Well, each time I'm going to need to store a bit, as an example, to represent was it true or false at this point. And then if it was true, I set a 1, for example. If it was false, I set 0. But that's just only going to make the constant for C slightly larger, only a little bit. It's not going to really increase the complexity of this. Well, here, this is just going to incur another c times f of n space for the initial configuration at the beginning. So ignoring the constants, what do we have? We have O of f of n recursive calls, and for each one, I have O of f of n space to store the possible configuration that it could be in. So f of n times f of n, guess that's f squared of n. Does this machine behave deterministically? Was there ever any non-deterministic choice made? No, it's trying every possible configuration deterministically. So in fact, M runs in the square of the amount of space deterministically, which is pretty awesome. So we actually can say something about how non-deterministic space relates to deterministic space because we can reuse space. We can't say the same thing about time because we can't reuse time. Any questions on Savitch's theorem and why it's true? So the details are not nearly as important as why is the overarching idea true? Any questions about why it's true? Yeah.
Is it kind of similar to NFAs and DFAs when we convert from like an NFA to a DFA, and we're keeping track of like separate computation paths of the NFA?
In some sense, yes. Yes. Yeah. Because we're not doing a recursive. Actually, we kind of are. Yeah. I didn't even think of that. So think about the NFA. So we do epsilon closure at the beginning. Then we have transitions that go out, and then we go down that road, and then eventually we're going to come back and try another transition out, and then we're going to eventually build the entire machine that way. I didn't even think of that. It's cool. So yeah, so the idea is just we're recursively building this machine, or simulating the non-deterministic machine. Any other questions though? Cool, I was happy we got through that. So I'll see you on Friday. Don't forget to pick up your test, please, if you haven't yet.